Hello again. Today I'm going to spend a little bit of time talking about these 4 meters. All 4 of these meters that I'm showing have something in common. They all have a wireless interface. On the far right I have my X-Tech EX540. This meter is produced by SEM. It's a model DT9939. To the left of it we have the Gossen MetroHit Ultra. Then we have the prototype 121GW, and on the far left we have the UNI-T UT181A. Now the X-Tech meter comes with its own radio. This is transmitting on the 900 MHz ISM band. They're using FSK modulation with this, so it's fairly simple to decode. I ended up writing some software for a spectrum analyzer that I purchased to decode this meter as part of a demonstration. Now the other 3 meters all use Bluetooth. Now the Gossen is using the older Bluetooth standard versus the BLE standard that these 2 meters use. Again, this 121GW is a prototype, and originally when this was sent to me the Bluetooth interface didn't work. David told me that up front. After they had released the Kickstart and they started supplying meters, I had asked to see if they were going to release the firmware for this. So there was a member on the EEVBLOG that had downloaded the image off of their meter, and then that allowed me to reprogram the radio that's in here. This is using a Blue Giga device. This is a BLE 112. So to reprogram this, I just bought this little TI adapter. It's cost about $20. This is the CC debugger. So it comes with this little interface cable. This won't work with this meter. This has a single inline connector, so I ended up having to make my own interface cable for it. So as soon as I got this thing programmed, I wanted to try it out. And of course I don't own a cell phone, so I ended up having to use the PC software. So the first thing we'll do is turn on the radio. You can see the Bluetooth indicator is on. You can start Dave's application. You can see it shows 2 instances of the 121. We'll select it, and you can see it's reading volts. 58 degrees, 57. Let's just change this to millivolts. So you can see it's tracking fairly well. So you'd like to be able to graph with this. Well, I don't think that this is really set up for a touch screen. You notice if I swipe, I kicked it over. Here's the graphing. Now if I try to go back, see, I'm not sure. I know I've had it switch back and forth before. You can hit restart. That'll wipe out the graph. Maybe reselect him. Nope. See, I have no idea how to run this thing. Isn't that crazy? You know, I can restart the program. I'll reselect the meter. And now we're back to working again. And let's try again. We'll select somewhere in the center. And again, no graph. Oh, here it goes. So I don't know if it's just I'm not waiting long enough. Let's try switching back again. Maybe you have to hold the panel for a very long time. Nope, that doesn't seem to be it. Now if I run this on a real PC using the mouse, this program works fine, but I thought the idea with this was to try to make it available on portable devices, and that would obviously include a tablet, but it definitely does not seem to be tablet friendly. So for me personally, when I'm running tests where I would use a meter like this for data logging, I would typically have it tied in with some other equipment. You've seen me run tests like that before if you watched any of my videos. So really what I was looking for was a LabVIEW interface for this meter. So I had asked if they were going to release an open API for the meter, something that was well documented, that basically you could use that to interface with this meter using any language you wanted. Unfortunately, nobody ever got back with me. So then I thought, well, I'll just go ahead and create my own interface for this. So I ran into a few snags with it. The first problem I ran into with it is the different versions of firmware use a different protocol. So when they first released the meter with version 1.0, they were literally sending all ASCII data across the Bluetooth interface. And they were sending a fair amount of data quite quickly, about every quarter of a second. So what ended up happening, I guess, is over time they realized that that Bluetooth interface was not reliable. So eventually they started shaving down the amount of data they sent across, and they also changed from sending ASCII to a binary format, and then they started slowing down the communications. So the way this meter is today, at least with this version 1.26 firmware, the meter only sends a complete packet every half a second right now. Now keep in mind that this meter has an SD card built into it, and the meter can actually log to that card every 200 milliseconds. So I thought it's kind of odd that they actually limit the Bluetooth interface to every half a second when they can actually record the data, much faster than that. So I used a few different tools to sniff the bus. So one of them is this little FTDI interface. This is nothing more than a USB to TTL converter, and I soldered this on the communications bus going between the microcontroller and the BLE112, and then I wrote some software for this to decode the bus. Another device that I picked up that proved to be pretty useful is this device from Adafruit. This is called the Bluetooth LE Sniff. Again, this just plugs into the USB bus. This allows you to use Wireshark to sniff the Bluetooth packets. This is fairly cheap. I think I paid like $25 for this. So once I was able to collect some data with Wireshark, one of the first things I learned is this meter actually sends multiple Bluetooth messages. That's not too surprising, but what's odd about it is the Bluetooth interface can send a maximum payload of 20 bytes. But the very first message that this sends out is only 1 byte long. Let me just show you what that looks like using a different program. This is Microsoft's Bluetooth LE Explorer. I'm just going to hit Discover, and here we can see the 121GW, and have a look. See, it's sending out 2 packets. You can see the very first one is an F2, and then followed by the rest of the payload. So that F2 is their start byte. Now keep in mind, it's not that they're actually just sending 1 byte. There's a whole structure for that BLE that has to get sent across. So there's a lot of overhead with them sending out that F2. And the rest of the payload is only 18 bytes. So they literally could have combined both of these messages into a single packet. So one of the nice things about doing it that way is BLE, actually like Ethernet, it has its own error correction built into it. And they could have actually ended up using that. Instead, what they have here is a checksum. So basically the way it works is after you stitch these 2 packets together, then you'll go ahead and validate the checksum. But what can end up happening is you could end up with like 2 F2s, for example, in a row, and that could happen if it drops a packet. And then of course the checksum isn't going to match. If you have one of these meters, these tools are free to download, assuming that you're running Windows 10. And Microsoft felt that the program could be useful enough that they went ahead and open sourced it. So you could actually make changes to this software if you want. Now, of course, my desktop PC doesn't have Bluetooth built into it. So I have one of these small dongles that just plugs into the USB port. And I'm using that to communicate with all 3 of these meters. So one of the things I noticed is even if I had the 121GW sitting right next to the radio on the PC, I would still see checksum errors. And that was actually kind of surprising. So I ended up taking the meter into another room of the house, and I couldn't even connect with this meter. So I brought out these 2 meters using the same PC, the same radio, same Windows 10, and sure enough it could find both the Gaussian as well as this UNI-T meter, but it couldn't find the 121GW. For whatever reason, this radio seems to be very weak. Now, I've asked other people who got involved with the Kickstart, and somebody else had run a similar test to see what kind of distance they could get out of theirs, and they were also complaining that the range on this meter was quite poor. So hopefully that's something that they can address in later versions of the meter. You can see the Bluetooth interface is enabled on all 3 meters. We'll go ahead and turn on the Bluetooth radio. There's the UNI-T. I'm quite a ways away from those meters right now. Continuing to get a little closer. There you go. I don't know, I'm probably 15 feet or so away from the meters right now. Again, all 3 of them are showing up right now. Again, as long as we're quite close to the meters, there's no problem. Let me just go ahead and shut these 2 off. So we just have the 121 enabled. So now we shouldn't be getting any interference from the other 2 meters. Okay, what we're going to do is switch this over to millivolts. So we've got some data, and we'll fire up Dave's application. can see it's reading it just fine. Of course, I'm right next to the meter. And I'm slowly walking away. Yep, this is about where it failed last time. Yep, again, it's not coming back. Yeah, I guess that's about 20 feet away. So I'm sure a few of you own the UT181A and you're saying this meter doesn't have Bluetooth, and you're absolutely right. It gets shipped with this small cable. Again, this plugs into the back of the meter, and then this just plugs into the USB bus, and they supply some software for that, and it works quite well. But if you want to use this with Bluetooth, they sell a separate radio. So this is it here. This is a part number UTD07A. So these are available on Amazon. So they claim that they support iOS as well as Android, but they also claim that they support Windows. But if you end up getting one of these, what you're going to find out is there is no Windows software available for this. And of course, I bought this with the idea that I could actually use this to communicate with a PC. Again, for me, using a cell phone to log data, it really wouldn't be of any use. But having this thing connected to a PC where I can use it with other test equipment, that would actually be a very powerful tool. So what I'm going to be showing you today is the software that I wrote to communicate with this using LabVIEW. So one of the problems with this meter, you can see it's plugged in right now. This has been charging overnight, and so you can see I cobbled up this little adapter that allows me to plug their charger in. This thing will run for, I think, about 40 hours between charges. I've charged this meter more in the last month since I started working on the software than I have the entire time I own the meter. So again, this thing should be fully charged. All we have to do is unplug this. So I have two different LabVIEW applications that I put together. One's for the 121GW and the other one is for the 181A. I'm not going to be demonstrating the one for the 121GW at this time because, to be honest, I think that this meter is still under development. It seems like every time you turn around, somebody's reporting a new bug. People were asking me once they started the Kickstart if I was going to look at one of the meters, and I had said at that time that, I felt that it was way too early and I was going to give it a year. I think that the Kickstarter started on the 3rd of December, so we're coming up on that 1 year real quick. And the last few times I looked on Dave's website, these meters weren't even available yet. So I think that they still have quite a ways to go with it before it's going to be released to the general public. Once it is available, I'll definitely have a look at it. So to get the interface sorted out on the UT181A, I ended up using another IR interface cable. So this just goes to the RS-232 port. Essentially then, once you've got that going, I could literally plug this adapter in with this one here. I'd end up just taping these two together, and I could run their software and sniff it with this. I also tried it with the meter, so I would have this thing dumping the data out, and then I could put this thing to the back of the meter like this and sniff the data. And the reason I needed all this working is I kind of had to have an idea how the protocol worked to sort this thing out. So again, I ended up using this Bluefruit with Wireshark, collected a bunch of data, and then from there I had the basics of this working. I ended up posting a very short video where I kind of showed the software in operation. There was no description beyond the title of the video. I think a lot of people probably didn't understand what was going on. But what came out of that is one of the viewers wrote me and said, hey, I wrote all this software, and he had done that in C and he made that source available. And so I wrote him, and he ended up joining me out in the forums. And so I ended up just asking him some very simple questions about the protocol on this, which he was able to answer, and he saved me a whole bunch of time. And then what ended up happening is a couple more people joined in. The original guy who wrote me ended up writing a little protocol specification for this meter, and with all that added information, I was able to get my software working with this meter in very short order. Now this device uses two AAA batteries. You can see it has an on-off switch. Turn it on, and it starts flashing the link. Now one of the things I found is that if you don't link to this thing, what will end up happening is it powers down. I don't know exactly how long, but it's probably within 5 minutes. So what I'm finding myself having to do as I was developing the software is I would go to connect to it. I couldn't. Have to turn around, switch the unit off, switch it back on, and then I could go ahead and link. It has another LED here. This one's red, and if the batteries get too low, that'll remain on. Now, I've only charged the batteries in this twice now, so this actually holds up quite well. You can see it has a small cover. It just snaps on over the back, and then again, this just slides over, cover like so. And the way that you activate this is the same way that you would use this cable here. Currently both meters are attached in parallel and they're connected to my function generator. Currently outputting a 10 volt peak to peak sine wave. So you can see each meter is changing between plus and minus 5 volts. The 121GW uses a Hicon chipset. It has a resolution of 50,000 counts and it samples at 5 Hertz. The documentation for the 121 doesn't show what the bar graph resolution of the sampling rate is. When they write data to the SD card, they can do that at the 5 Hertz rate. However, when you're using the low energy Bluetooth, the meter only transfers data at 2 Hertz. Compare that with the UT181. This meter uses a device from Cyrus Tech. This chipset has 2 A to Ds built into it. One is for the bar graph and the other one's for the primary display. Primary display is 60,000 counts and the bar graph is 600 counts. The bar graph gets sampled at 20 Hertz on this meter, but the primary display is only updated twice per second. On this meter, they transfer the data across the BLE interface at 10 Hertz. However, because the primary display is only sampled at 2 Hertz, what you'll see with this meter when you're looking at the primary display is every 5 samples will be identical. So currently the frequency of the function generator is set at 100 millihertz. That gives us a period of 10 seconds. So for the 121GW, this gives us 20 samples across the entire waveform. And again, that's because of the limitation of the 2 Hertz update rate. And because the 181 actually samples at 2 Hertz, we also end up with 20 samples across the entire period. However, when we're looking at the low resolution A to D, which is actually being updated at 10 Hertz, we'll end up with 100 samples across the period. So let me just go ahead and enable the Bluetooth. Again, you can see the icon is now active. This is looking at my software for the 121GW. You'll notice that there are 2 LCDs on the top. The one on the left represents the primary display. The one on the right represents the secondary display. You can see the meter is currently outputting 60.7 degrees Fahrenheit. In the upper right of the graph, there's some metrics that are being updated live. This includes the minimum, the maximum, the standard deviation, and the mean. If we want to plot the secondary, we can do that here. So this is a plot showing the temperature change. I also have the ability to record data. This will create a CSV or a comma separated file. So this is low Z. Currently outputting 20 volts peak. I guess the meter can't pick this up. Let's just switch it back to AC volts. And there you can see it's 7.07 and it's at 60 Hertz. We'll go ahead and switch the meter to resistance. And you can see this is a 0.496 ohm resistor. I used this for some previous tests that I ran with this meter. So again, the software would be pretty good for doing drift studies and whatnot. Originally, when I first received this meter again, I didn't have the ability to offload the data using the Bluetooth. So anytime I wanted to do some kind of a long-term test like this, the only option I had was to record to the SD card. So I was essentially running this meter without the back cover on. So the rubber boot was removed, the back cover was off, and the meter was wide open. And the reason I do that is because I'm swapping that card in and out, and there really wasn't any other option. As I understand it, they don't have any provisions for offloading that card over the Bluetooth interface. If they were to support the Bluetooth as far as downloading, unfortunately, the way the meter's set up today, it would be far too slow to do those transfers. Again, essentially you're sending 20 bytes of data. It's actually 19, but they're doing that in a half a second. So you could imagine, even if you're going to send a couple of K, how long that's going to take. Now, this software does have some post-processing available. I've used this to run various tests on the 121. So as far as post-processing, I not only support this meter, I also support my SEM meter, as well as the UT181, the UT61, my HP bench meter, and my Gauss and Metrowatt meter. You'll notice that the 121 is listed twice, and that's because I have the ability to import the CSV files that this meter generates on the card, as well as, of course, reading through the Bluetooth interface. So these same features are built into my software for the UT181A. I'll demonstrate them in the software for this meter. Let me go ahead and we'll fire up the software for the 181. Okay, before we do that, we have to enable the Bluetooth. We do that by selecting Set, Communications, turn it to on. Again, you can see the icon in the upper right next to the battery. We'll go ahead and turn on the radio. Alright, let's go ahead and select Link. You can see on the left we have the device name is the UT-UT181A. The manufacturer is ISSC. The model number is a BT5050. And the hardware revision is 5050 BLE-TR. Let's go ahead and select Run. You can see with this software we have 4 LCDs. These are enabled and their functions changed based on the menu or the function of the meter. So currently the upper left LCD is showing the primary display, and that's in volts DC. And the upper right is showing the bar graph, and again that's in volts DC. Again, this A to D only samples at 2 Hertz, but again you can see the meter is outputting data at 10 Hertz. So as I had mentioned earlier, you'll end up with 5 identical samples before the meter actually updates. Now if I go ahead and plot the bar graph data, you can see that's very smooth. Again, that's because the bar graph is updating at 20 Hertz. So for every sample that the meter outputs, we get an updated value. So if I were to slow the frequency down, so now what you can see is the red trace, which again is the bar graph, which looked to have a finer resolution, now actually has a lower resolution. And that's because the time that this thing updates is very fast, but it actually is a lower resolution A to D. So for lower frequency signals, we'd like to be able to use the higher resolution A to D on the primary display, but it'd be nice if we could leverage the 2 A to Ds that we have. Alright, so again the UT181 has 2 A to Ds built into the main chipset. One of those is a high resolution low speed A to D. The other one is a very fast A to D, but it has a very low resolution. So what I'm thinking is that we could combine those 2 A to Ds where we could obtain essentially a very fast A to D that has a high resolution. If we look at the low speed A to D, again it updates 5 times slower than what the fast low res A to D is. So essentially what you end up with is 5 data points that are all identical, and then it switches to the next data point. Where the high speed A to D, you'll actually end up with discrete samples. Again, that fast A to D samples at 20 Hertz compared to the low resolution A to D, which samples at 2 Hertz. But again, the meter only updates every 10 Hertz, and that's across the BLE. So if we were looking at, for example, DC, we could just use that high resolution A to D all the time and it would be just fine. But if the sample were to change, what we would want to do is use the high speed A to D in this area here. So this would be high speed, low res. But then in this area down in here, we'd be using the low speed, high res. And the same thing up here. So essentially what we end up with is a very fast A to D with a very high resolution. So one way again to do that is to look at the slope. So I'm thinking is for the high speed A to D, we'd have 2 windows and we'd look at the average inside of each window, and then we could compare these 2 averages to calculate the slope. And then what we could do is have a threshold, so as the slope were to change, eventually it could reach some trigger point, and that would allow us to transition over to the high speed A to D. And if the slope is less than that, then we're switching over to the low speed A to D. So I went ahead and implemented this, but there's a problem with this. You know, if we have a waveform that looks something like this, and let's say this is our low speed A to D, and maybe the slope is right here that I'm trying to trigger off of. So let's say right here is our transition point. The problem that we have now is this thing is using this nice smooth high speed A to D. We hit this point here and we say switch to the high resolution device. It's going to cause this spike in the data, and then we're going to see another step, and then it'll flatten out. So what we'd like to do is get rid of this area here. So at the point when I say go ahead and transition to the other A to D, I say what's the difference between these 2 signals? And if that difference is greater than another threshold that I set, then I'll continue to use the high speed A to D until these 2 points converge. So essentially in this case, we'd be using the high speed A to D up to this point here, and then we switch over to the low speed A to D. and we'll continue to use it until, again, the threshold is met for the slope. So let me show you how that works. Okay, the way we select that is by enabling this blend signal, but for now let's just go ahead and enable that on the chart. So currently you can see if I disable the primary display, you can see it's actually using this blended data. Let's go ahead and change the frequency of our waveform. So right here you can see it's just about ready to transition. Slope's changing, and pretty soon it should be going over the high-speed converter. Right there's the transition point. Again, as we start to reach the bottom, you'll see this thing again change over to low speed, high resolution A to D. Right there it started to switch. And now we are using the high resolution A to D. Again, let's go ahead and zoom out. You can see this is quite a smooth transition. Now these can be tuned through these parameters here. The one is the slope, the other one is the transfer difference. Let's go ahead and increase the frequency. So this is our 100 millihertz. Again, this is what the data would normally look like. And let's go ahead and enable the blending. Once this is enabled, all the data that's stored to the disk is also stored as blended data. We can also do blending as a post-process. We go ahead and increase the frequency. This is with a 1 hertz signal being applied. Okay, let's rescale the x-axis. Here we are at 2 hertz. And this is at 4 hertz. You can see it's starting to alias pretty bad. So I'd mentioned that these other LCDs have various functions depending on what mode the meter's in. For example, let's select min-max. So now you can see the upper left is the current, the upper right is the maximum, and now instead of displaying volts DC, for example, you can see it's displaying the time. These numbers are shown here on the right hand side of the meter. This is when it's actually met that criteria for whatever the maximum was. You can see the average updates on every sample. We have a resolution of 1 second. Let me just disconnect our function generator and we'll switch this over to resistance. And you can see it's displaying roughly 55 ohms. And you can see for the units now, the software is displaying the omega symbol. If we select relative mode, you can see our reference is now at 55 ohms and our relative resistance is at 0.78 and the absolute is 54. Let's go to menu again and let's select AC plus DC, and let's again attach this to our signal generator. Again, on the upper left you can see we have the primary display. Second display is the auxiliary, and that's in volts AC. And the third display is the secondary auxiliary channel, and that's the DC. Again, all these can be plotted separately. So this is looking at the DC value. Let me just dial down the amplitude, and then we'll add an offset. So you can see we're now at basically 2.5 volts offset. Go back to the primary display. Let's change this over to DC, and let's reduce our frequency. And you can see what's happened is instead of switching between plus or minus 5 volts, we're now switching between 0 and 5 volts, and this is why we're seeing a 2.5 volt offset. So let me show you some other features with this software. So again, all this data can be recorded, and I have the ability to post-process some of this. So let me just show you that. So if we go under post-processing, these are some of the menus. Let's go ahead and add a waveform. So here I'm sweeping the function generator between 100 millihertz and 10 hertz, and I'm doing that over a 500 second period. So we would call this a chirp waveform, and you can see it attenuates as the frequency is increasing. So if I select the chirp function, this is plotting the attenuation versus the frequency. So you can see at 1 Hertz we're basically 4 dB down. At 10 Hertz we're all the way down to 34 dB. Let's just flush this data out and let's load a different waveform. So this is with the blending enabled, and you can see it's basically flat. Let's just zoom in on this a little bit. So again, I'm slowly increasing the frequency as I'm sweeping through it, and eventually the meter is going to start to alias. Let's go ahead and we'll re-zoom out, and let's look at this with our chirp profile, and you can see it's basically flat. So at 10 Hertz now, instead of 34 dB down, we're at 0.16. So let's go ahead and load up a square wave. You can see this is a square wave with a 5-volt peak, and it's got a period of 100 millihertz. Let's switch this over to 3 dimensions. You can see basically what I'm doing is I'm taking slices of that data and then I'm laying it on top of one another. If we look at the histogram, you can see it switches at +5 and -5. This is looking at the Fourier transform for the data, and this is looking at the jitter. So what I'm doing here is I have a software phase lock loop, and that's trying to track this square wave, so that phase lock loop will have very low phase noise. And what we'll do is we'll compare the deviation of the raw data against that phase lock loop. So this is looking at an overlay of all the data. We view this in 3 dimensions. This is what it looks like. Let's have a look at the eye pattern. You can see the variation is about a half a second. So watch what happens if we try this same test, but we're going to enable the blending. And let's look at the 2D edge now. You can see it's right on top of each other, and this is the eye pattern for it, and you can see it's basically perfect. And again, that's because the meter is updating at 10 Hertz. With our waveform having a period of 100 millihertz, the extra samples actually cause us to tighten this down quite a bit. So I'd mentioned earlier that I had the ability to import data from various meters, so I've gone ahead and added support for my SEM meter as well as the 121GW. This is a resistor that I had made up some time ago to run some tests. This is a part by KDAC. It's a TK series. It has a temperature coefficient of 10 ppm. This is the resistance that I measured with my HP bench meter at 21 degrees C. So in these graphs I'm showing all 6 meters measuring the same resistor. I think I had all these meters set for sampling at 1 second intervals, so it's basically 1500 seconds. So a fair bit of time to stabilize. So some meters like the UT181A here, I didn't allow the temperature stabilize at all. I just turned it on and started collecting data. Now my HP meter, that's the one in yellow, I had actually left this thing on for I think about an hour before I took the data. Actually it shows right here. So there was a 2-hour warm-up, and you can see the UT181 was a 0 weight. Same thing for the UT61E. The Gauss and Metrowatt was a 10-minute warm-up, and that's the white trace. Now again, that Gauss and Metrowatt is a 300,000 count meter. Out of all the meters that I purchased, that's about as close as I've came with a handheld meter to matching the performance out of my HP bench meter. This red trace on top is my SEM DT9939. The trace just below it in purple is the 121GW prototype. You can see that I've allowed it 5 minutes of warm-up, and you can see it starts out drifting quite a bit. Now again, this meter is a prototype, and we know that one of the things that they changed in the final design was the voltage reference. So I'm expecting that the meters that were delivered as part of the kickstart would have a better temperature coefficient than what this prototype meter does. I think that's going to be it for this video. I hope you enjoyed it. Again, if you have any questions about the UT181A or the Bluetooth interface, feel free to ask. I'll go ahead and provide a link to the EEVBLOG thread where we were discussing the protocol. Again, if you're interested in writing your own software, I'd suggest you start there. So before I end this video, another question had come up. Somebody's asking about grease, and that comes up from time to time. I did a video once on using WD-40. That came about after another member had posted that they were using WD-40 on their switch contacts. You know, I'm always amazed what people are doing with some of their meters. Anyway, this is the Fluke 107. Now this meter has been exposed to higher voltages than any meter that I've ever received I did end up damaging this meter eventually, but I wanted to show you the switch contacts. So if we look right here, if I can get in some decent light, you see that the contacts on this are actually greased. See that? One person had said, well, the only time that they've ever seen grease is when it goes into this detent area, you know, and then maybe it migrates down onto the switch contact. So the obvious thing with this meter is, of course, the knob is on this side and the switch contacts are obviously on the opposite side. So that's not something where the grease migrated from this area onto the circuit board. Fluke added that grease for some reason. I'm not sure why. Now, if you're not aware, I ran some life cycle tests on a few different meters where I was basically rotating the switch back and forth, and I was putting 50,000 full cycles on these meters, and the meter that performed the best in that test so far was a Fluke 17B Plus, and that meter uses dry contact, so there's no signs of any grease on it at all. And a lot of the meters that I test don't have any grease on them. Some meters like this Fluke 107 have had the grease, have performed very well in my transient testing, but again, a lot of the meters I've tested that have performed equally as well don't have any grease on them at all. The same holds true for the meters that have done very poorly in my transient testing. A lot of those meters had grease in them. They couldn't even survive the transients off this low voltage transient generator. So a member named Fungus had asked, along with another member 001, if I could run some kind of test. Member 001 is actually asking about using Vaseline on their circuit board. I couldn't believe that when they wrote that because, you know, Vaseline has a very low melting point. We'll do a little bit of an unscientific test. You just put a little bit of this on this plate. Alright. All I'm going to do is just heat this up right there a little bit with this lighter. Look at that. See that? Just that little bit of heat. It's already liquefied this. So if you put this on a meter and you put it out in the sun, that stuff is just going to drip right off of the circuit board and it's going to end up wherever. This is not what you'd want to be using inside of a meter under any circumstance, but for whatever reason they feel that, I guess that's something they'd like to try. So they had asked me about performing a test with this Vaseline, and I said if you could at least write up some sort of a description, maybe I could look into it. Well, another member, Fungus, had basically just said set up a gap and, you know, apply a voltage across it, get it to where it breaks down, apply the Vaseline across the gap, and then just see what it takes to make the gap break down again. You may remember this circuit board from a previous test where I was testing some 4.7 mega ohm resistors. Actually, I had one of those flame out pretty good in that video. What I'm going to do is just clean this gap out before we do anything else with it. So I'm sure it's got my finger goob all over it. Alright, let's go ahead and turn up our power supply. And you can see there's about 2,000 volts right there. Right there, about 2,500 volts. I think that's where it broke down last time. You can see this is re-solidified. Lab's a little cold. I'll just put a liberal amount on there and let's see if that's changed the breakdown at all. There's 25, 3,000, 4,000, 4,500. It's actually breaking over to the ground. Tell you what, I'm going to add a little more. Normally we'd be using this stuff. This Corona dope. Alright, let's try it again. So there's almost 6,000 volts. That's the limit of what I can get out of this. Unfortunately, The downside of producing a video like this is, you know, there's going to be people out there that think, yeah, I'm just going to cover my meter with this Vaseline and that's going to be the best thing ever. My meter's going to survive, you know, 6,000 volts now. Obviously, that's not going to be the case. If you're one of those people, you know, don't play around with high voltages and high energy circuits. That's all I got to say about that. So all I'm going to do here is tilt the board up on its side. It's quite common for these to sit upright. Let's go ahead and turn the power supply back on. We'll just set it for 3,000 volts. See, I have the heat gun out. Let's just heat this up a little bit and see what happens. And if you look, you can see it's already starting to solidify. And I should mention too, this Fluke 107, I actually damaged it a couple of times, but I have repaired it and it is 100% functional. I keep it around in case I decide to use it for a future test. It's actually a pretty decent meter. It's similar to the Fluke 101, except you can see it does have a current shunt built into it. And I'm sure people are either going to ask me what grease would I recommend or what's inside of this Fluke 107. Of course, you're free to write the manufacturer and ask them. You could probably do that just as easily as I could. I actually do have some dielectric grease that I like to use. That's what this stuff here is. You can see it looks similar to the Vaseline. Let's do the same test with our cigarette lighter. If you could see this. And you can see I've definitely heated this up and that grease is not changing states at all. I mean, this is hot. See how that stuff just stays put? So this dielectric grease was produced by General Electric. It's purpose made for electrical use. This stuff, my wife uses this to remove her makeup. I guess if you're one of these people who dress up your meter and you want to try to remove its makeup, that would be a good choice. Let's try putting some of this on our little test board. So you can see I've taken our Corona dope and I've doped up the edges of this. Should start breaking down somewhere around here. There you go. And I'm just going to apply a little bit of this grease. Similar to the thickness of the Fluke 107. Alright, let's try turning up our voltage now. See, we're all the way up at 6,000 volts. No problems at all. We turn this back down. And again, I'm going to put the board on its side. And again, we'll turn our supply voltage back up. Set it for 5,000 volts. And again, we've got the heat gun. Again, I doubt very many people that work with high energy circuits are going to trust their lives to Vaseline. But you never know. I mean, you don't want to be the person that goes to the hospital because you got injured and have to tell the doctors and the attorneys, yeah, I was watching this Joe Q. Smith YouTube channel. Seemed like he knows what he was doing. And he was demonstrating the electrical breakdown when using this Vaseline. And boy, I just thought that stuff was great. So I did it to my meter and here we are. And that's if Darwin doesn't get you. Well, I think that's going to be it for this video again. So I hope you enjoyed it. Till the next video. Later.